Hi and welcome to Trig Formulas Day 6. Today we're going to be working with our Pythagorean identities. And if you remember those, that is cosine squared theta plus sine squared theta equals 1. And then if we go through and divide everything by cosine squared theta, we'd get 1 plus tan squared theta equals secant squared theta. And instead of dividing by cosine, if we divided everything by sine, we would get, or sine squared, we get cotangent squared theta plus 1 equals cosecant squared theta. And those are our three Pythagorean identities that we will be using. Remember, we've talked about just subtracting and getting things in terms of cosine squared or sine squared. So we have cosine squared theta equals 1 minus sine squared theta, and then sine squared theta is equal to 1 minus cosine squared theta. You can do that with the other two, for example, and move them around if you needed to. If you were to subtract 1, you'd get tan squared theta is equal to secant squared theta minus 1, or vice versa. With the other one, we'd have cotan squared theta is equal to cosecant squared theta minus 1. So those are all different forms of the identities that we can use to solve these proofs. So in number 1, we have sine squared theta over 1 plus cosine squared, or 1 plus cosine theta equals 1 minus cosine theta. Well, do what we got to do. Since I have cosine on both sides and a sine squared, I'm going to change it into terms of cosine. So for this one, I'm going to say cosine squared theta, 1 minus cosine squared theta. And place the sine squared theta, because I got that from up above, what I wrote on the side, over 1 plus cosine theta. Now it looks like we can just go ahead and cancel things out right away, but we can't. I don't know if you remember, but a couple days ago we talked about factoring some of these things. And the top, the numerator there, is actually a difference of two perfect squares. And it is a 1 plus cosine theta and a 1 minus cosine theta all over 1 plus cosine theta. Now this entire parentheses cancels out with that, and I'm just left with 1 minus cosine theta, and that's what matches. It says, what values in 0 degrees between 0 and theta is between 0 and 360 make the above identity undefined? Well, where's the only place that we have a denominator? It's 1 plus cosine theta. And our fractions are undefined when the denominator is equal to 0. So solve that, and I have cosine theta equals -1. And cosine is equal to -1, if you remember your unit circle or which trig graph looked like, at 180 degrees. Right, for number 2, cosine squared theta is equal to secant squared theta minus 1, or sorry, times secant squared theta minus 1 equals sine theta. Well, let's see here. There's a couple different ways we can go about this one. I can make a simple substitution. Instead of secant squared theta minus 1, I can put tan squared theta, so I can shorten that. So cosine squared theta times tan squared theta. Now turn that into terms of sine and cosine. And that would be sine squared theta over cosine squared theta. And this should actually be sine squared theta. That's a typo. My mistake now that I look at my notes. My two cosine squared thetas cancel out, so I'm just left with sine squared theta. Otherwise, I wouldn't be able to solve that if I didn't have that. Alright, next page. Sine squared theta is equal to cosecant squared theta minus 1. Or sorry, sine squared theta times cosecant squared theta minus 1 equals cosine squared theta. Well, sine squared theta and cosecant squared theta are reciprocal functions, so I can rewrite this as sine squared theta times 1 over sine squared theta minus 1. If I distribute my sine squared theta on the outside, hang on, just distribute that. These two will cancel out, so I'll have 1 minus sine squared theta. And looking on the other side of our sheet, 1 minus sine squared theta is equal to cosine squared theta. Again, lots of times there's more than one way to solve these. Oh dear. We have our number 4. 1 minus secant squared theta over 1 plus secant theta equals cosine theta minus 1 over cosine. Well, I know that the left-hand side in the numerator I have a difference of two perfect squares. So it's 1 minus secant theta times 1 plus secant theta all over 1 plus secant theta. Now those cancel out. I'm left with 1 minus secant theta. That does not match the other side, but I can do some work with cosines and secants. If I look at this as a pretzel, I have 1 minus whatever cosine is secant theta. So now they match. Ooh, number 5. Oh, this will be a fun one. On the left, I have two fractions. And on the right, I have a single term. Well, the left side's a little bit more complicated, so I'm going to work with that one because the only thing the right side's going to give me is a 1 over sine squared theta, and that's not really going to help me any. So I'm actually going to have to work with the left side first, and I have to be able to add those two fractions. And in order to be able to add those two fractions, I need an LCD. And my LCD here would be 1 plus cosine theta, 1 minus. Yikes, can't even write. 1 minus cosine theta. So the first fraction is missing 1 minus cosine theta, so I'm going to multiply the top and bottom by 1 minus cosine theta, so I'll get 1 minus cosine theta over 1 plus cosine theta, 1 minus cosine theta. Plus, this one is missing a 1, can I write just once, 1 plus cosine theta. Okay, that looks horrible, I'm sorry. I can combine like terms in the numerator. My cosine thetas cancel each other out, and I'm left with 2 over 1 plus cosine theta times 1 minus cosine theta. And it's still not quite where I want to be, but I have a 2, so things are looking up if I look at the right-hand side. 1 plus cosine theta, 1 minus cosine theta is a difference of two perfect squares already factored. So if I were to multiply them, I'd get 2 over 1 minus cosine squared theta. And 1 minus cosine squared theta is equal to sine squared theta. And on this side, I have 2 cosecant squared theta, so it's the same thing as saying 2 over sine squared theta. So now they match. I could have changed the left-hand side to 2 cosecant squared theta, but sometimes it's harder for people to go backwards like that. But pretty much that's it. The only difference is today where we're using our Pythagorean identities to kind of help us out. So we can do the difference of 2 perfect squares, factoring it or foiling it. Either way, use it to our advantage. And just rewriting our Pythagorean identities in a form that we can use them and make substitutions in. But that's it for today.